Welcome all to Facilities Design and Logistics course. We continue our discussion on discrete facility location problems. If you remember, in our previous lectures, we started talking about these discrete facility location problems, and we have seen uncapacitated facility location and capacitated facility location problems. And also we have seen a greedy heuristic algorithm that we use to solve uncapacitated facility location problems we solved in our previous lecture. In today's lecture, we will continue to discuss other alternative discrete facility location models. These models that we discuss here, that we see here, they are some kind of base models. For example, the capacitated facility location problem. It is a very common, very well-known problem, but the version that we formulated here, it includes only the basics model. But in real life, you may have additional restrictions, additional constraints, or different objectives. So having that base model, you can include these additional restrictions, constraints, or objective functions into that model. So actually, when we say discrete location problems, there are not just 5 models like this. There are many variations of these models, but the models that we see here are the basic models. Okay. So let's get started. The next model that we will talk about is the so-called P-median problem. Okay. So the name given to this is P-median. Why it is P? Because in this problem, we want to establish or open exactly P facilities. So P here comes from this P, which is the number of facilities that we want to open, and it says exactly P facilities. So it can be, for example, open exactly 3 facilities or 5 facilities. An assumption in this problem is this: each potential location, the candidate locations for the new facilities, has the same fixed cost. So the fixed cost in capacitated or uncapacitated facility locations, we were assuming that establishing a facility at location, alternative location or site J was Fj. But here, all Fj is equal to F in P-median problem. It means that it is not different depending on the candidate sites. It is all the same, just F. Okay? So therefore, these fixed costs does not create a difference between establishing a facility to here or there. A restriction on this problem is to satisfy the demand of all customers. So we want to establish P facilities to satisfy the demand of all customers, and our objective is similar to the previous one, is to minimize the total cost. But the total cost, again, since the fixed costs are the same for all candidate sites, you don't need to include these fixed costs. So we will formulate this problem. And then we will formulate another problem which is called P-center problem. These P-median and P-center problems are very similar to each other, but the only difference is the objective function. Okay? So first thing first, how do we formulate it? We start formulating by defining the decision variables. And actually, in uncapacitated, capacitated facility location problems, we used 2 types of decision variables. One variable to indicate if we open a facility at site J or not, a binary decision variable. And we represented this variable, let me write it here, by Yj, and we said that it takes the value of 1 if a facility is opened or established at site J. So this J indicates the alternative or candidate locations, and 0 otherwise. And we use this actually to calculate, let's say, the fixed cost of the facilities, and also we establish the relation between this decision variable, whether to open a site open a facility at site J or not, with the other decision variables that we have. And remember how we defined our the other decision variable as xij. We said that this is the proportion of the demand, right? Proportion of the demand at customer site I satisfied from let's say a facility opened at site J. So actually here I represents the locations of the existing facilities or customers. So here again, let me repeat, when sometimes I may call it a customer, sometimes I may call it an existing facility, they are the same thing, okay? And J indicates the candidate sites. So these were the two types of decision variables, and actually we will use same decision variables in P-median and P-center problems. Okay, so the decision variable definitions will be yj and xij. The next thing to write is our objective function. And in P-median problems, we try to minimize the total cost. Let me write minimize total cost. And again, similar to the previous models that we formulated, there is a fixed cost of establishing a facility, but this fixed cost is the same. So remember how we formulated the previous problem, okay? Remember we said that it is summation over j from 1 to n if there are n candidate locations, and then we multiply this fixed cost, it was fj, with the yj variable if we established a facility or not. But in this problem we know that this fj is equal to f. All of them are identical, so we don't need to use the j index here. And then plus, okay, the second part is with respect to the cost of satisfying the demand of a customer from an existing facility. And we said that, okay, if this is customer I and if this is facility J, and if we establish this facility and satisfy xij proportion of the demand of this customer at this location, then the cost will be Cij. If we satisfy 100% of the demand, it will be Cij. If we satisfy xij proportion of the demand, then it will be xij times Cij. So the second part is summation over all I 1 to m. M is the total number of existing facilities, and j goes from 1 to n. So these total number of existing facilities, this m, and this is the total number of candidate sites. Okay, then it will be Cij times Xij. This is the same, exactly the same objective function that we have written for the capacitated and incapacitated facility location problems. The only difference is the index of f. We don't need that anymore. Subject to. Okay, what are the constraints? Look, we have to satisfy the demand of all customers. This is the same with the previous cases. And how do we write it? For all customers, I from 1 up to m, I need to satisfy their demand. So this xij, summation of xij over j, should be equal to 1. So remember, this xij is the proportion, and then the sum of these proportions should add up to 100%. Okay? Now there is this constraint over here. It says that we will open exactly P facilities. Okay, P facilities. Look, this Yj represents if we open a facility or not. So let's assume that the candidates, we have candidate 1, candidate 2, 3, up to we have n candidates. Okay, then if this is 0, y1 is 0, let's say this is y1, then we don't establish this facility. If y2, for example, if it is 1, it means that we establish it. y3, yn, if I go in this way, it is not established, then this is established, then etc. So how can I get the total number of facilities that I opened? It is actually the summation of these values. If you add up these zeros and ones, their summation will give you the total number of facilities that we establish, and we want this total number to be equal to P. Okay, actually your constraint, our constraint that we want to write is the summation of Yj should be equal to P, and if we write it in compact form, j from 1 to n Yj should be equal to 1. And in previous models, we established the relation between xij and yj, and we still need to use the same relation. What is that? If a facility is not opened, for example y3 is 0, it is not opened, there is no such facility, then if this is customer A, this x0, let me write number instead of a letter, let's say that this is customer 5, then x05, the proportion of the demand that we satisfy from this third facility, it should be 0. Okay, so if yj is 0, then the corresponding x should also be 0. Then actually we have written it in two different ways. You can use both of them. I'm going to write only this version. Yij is less than or equal to xij less than or equal to yj for all I, for all existing facilities, and for all candidate sites. Actually, the other version that we have written here was like this: xij summation over I 1 to m should be less than or equal to m times yj. So you can use these both versions here. And last thing is the decision variables. The decision variables xij are continuous, greater than or equal to 0, and yj are binary decision variables for all I and j. Actually, this xij, we said that they are proportions. We can satisfy the demand proportions. And remember, in incapacitated facility location, it was we said that although it is greater than or equal to 0, when you solve it, you will get either 0 or 1. Actually, look, I have written this wrong. Be careful. We said that this summation is equal to P. I want to establish exactly P facilities. If you write here 1, it means that you want to open only single facility, only one. But here, we want to establish P facilities, so this should be equal to P. Okay, so this is the model. Now there is one observation. Look, in this objective function, look at this site over here. And let me clean up this space over here. In that summation, fj doesn't include any index f. So this summation is j equals 1 to n f times yj. Since there is no j index here, it is just a constant, it's just a number, let's say 1000. You can just take it out and you can write it f j from 1 to n yj. Okay, and look at this side over here. As a constraint, we say that this summation must be equal to p. So you can replace this one by p, and what do you obtain? You got f times p. This is a parameter. It is the cost, fixed cost. This is a parameter. It is the number of new facilities that we want to establish. So actually in your objective function, here you don't need to write this one, but just write p times f. And actually, if there is such a constant in an optimization model, you don't need to write it into your model at all. Just delete it, solve the model, you will get the optimal solution. And if you want to find the final total cost, you need to add this p times f to the total objective function value. Therefore, we never represent or we never write the constants in the objective function, and simply we got this objective function, which is the minimization of Cij times Xij. Okay, so this is the P median problem. Again, remember the assumptions of the problem. We want to open exactly P facilities. The facilities have the same fixed cost, and we want to satisfy the demand of all customers. If the facilities doesn't have the same fixed cost, we cannot delete this first term of the objective function. You have to have it there, and then the rest of the constraints will be the same. Okay, but the known P median problem in the books, in the literature, is this one. Okay. The next problem that we are going to consider is actually the P-center problem. Okay, P-center problem is very similar to the P-median problem. And remember, in that problem, this P represented the number of facilities that we want to open. So we will open exactly P facilities. And then the fixed cost is the same again. We want to satisfy the demand of all customers. These are the same. But what is different? Only difference is the objective function. The previous problem, the P median problem, is a mini-sum objective, minimize the sum of the costs. But the P-center problem is a min-max type problem. Okay, therefore actually the names are different, P-median and P-center. Here the facilities that we are establishing with such an objective tries to be in the center of the customers, okay, customer locations, at a central place. The other one, they try to be in the median of the existing facilities. Okay, the objective function changes the optimal solution. And here, actually, all the constraints are the same, the decision variables are the same, but the objective is different. So we still have this yj as 0 and 1. I will not write the definitions, and xij. But there is one difference here as a result of this objective. This xij is also 0, 1 in P-center problems. What does it mean? We are forcing each customer to take service from one of the new facilities. We are assigning each customer to a single facility. Okay? One, if customer I is assigned to facility J, and it will take 0 otherwise. And look, these two variables, this yj represents the location of the new facility, And this Xij represents the allocation of the customers to the facilities. So usually the models, the location models that includes this Yj and Xij, we can refer to them as location allocation models. Okay, so the uncapacitated facility location, capacitated facility location, P median, P center, all of these use these type of variables Yj and Xij, and we are trying to locate new facilities and allocate the customers to these new facilities. Therefore, they are called location allocation models, all of them. Okay, now let's try to write our objective function, and as I said, this objective is a minimization of the maximum. Okay, what maximum of what? Let's assume that we have these existing facilities, the customer 1, let's say customer 2, customer 3, and etc. So we want to locate a new facility so that when we allocate, let's say this is another new facility, when we allocate this customer to here, we have a cost. Let's say this is new facility 1, this is new facility 2. So the cost of allocating this second existing facility to second new facility, the cost is C22. And let's say that this is cost is C11 and this cost is C31. And what we try to do is we try to minimize the maximum of these costs. Okay, minimize the maximum of C11, C12, and C22, C21, and C31, C32 actually. Okay, but of course this cost C11 becomes a cost if this customer is allocated to this facility. Therefore, we need to know whether this customer is allocated to that facility or not, and we understand it by the decision variable x11. So we want to minimize the maximum cost per each facility or each customer to assign to a new facility. And let me write our objective function. It will be minimize maximum. Okay, let me write it in open form first. C11 times x11 and C12 times x12, and it goes, let's say, up to how many existing facilities or customers do we have? M. Cm n times xmn. Okay, so I'm not adding them up. I'm trying to find the maximum of these multiplications. And if I want to write this in compact form, I can write like this. Minimize this maximum of I from 1 up to m and j from 1 up to n, Cij times Xij. Okay, I am trying to minimize this value. And subject to the constraints, all demand of the customers must be satisfied. So for all customers, their summation over j up to n, Xij should be equal to 1. So we need to satisfy the demand of all customers here. And then we need to open exactly P facilities. Therefore, that constraint is also the same. Summation of this Yj, j from 1 to n, should be equal to 1, should be equal to P. We want to establish P facilities. And then Xij should be less than or equal to Yj, exactly the same constraint for all I and j. And then Xij as well as Yj now must be binary. Okay, for all I and j. So the only difference of this model from the P median is the objective function and this restriction that this xij is 0, 1. In the previous version, actually, we still have that restriction, but if you don't write it, I mean, if you don't say xij should be binary, but just write xij greater than or equal to 0 and solve the model, again, you will obtain either 0 or 1. You will not get allocate a customer to different new facilities. And the reason for this is, look, in this p-center and p-median problems, we don't have capacities. And remember, in the uncapacitated location problem version, if we don't write this xij to be greater, to be binary 0 or 1, but just write they are greater than or equal to 0, you still obtain optimal solutions as xij being 0 or 1. This is the same. But if you had a capacity restriction here, like the capacitated facility location problem, then you cannot talk about this property. Okay, so this is the p-center problem, and this p-median and p-center problems are well-known problems, much studied problems. In books and if you search in the internet, you will find a lot of research and studies on this. Okay, another problem version that we will consider is named total covering problem. And actually, if you remember our operations research course, OR2 course, we have formulated this problem. So what is total covering problem? Let me illustrate this problem with an example. Assume that there is a retail firm, and this retail firm considering a change in its distribution system. So in the past, this firm was shipping merchandise from the distribution centers to the stores on a weekly basis. So in each week, they were sending these items to the stores, to the shops from the distribution centers. But now they want to establish distribution centers, open new distribution centers, so that they will be shipping to the stores within 24 hours. Okay, within 24 hours. Now there's a table over here which consists of zeros and ones. On the rows we have the stores, and on the rows and on the columns we have the distribution centers. And this table is a matrix of so-called cover coefficients for the 10 stores. You see there are 10 stores and 10 potential sites for distribution centers. So what does these zeros and ones indicate? If this value is 1 over here, it means that this distribution center 1 can serve this store 1 within 24 hours. They can ship. For example, this is 0. What does it mean? It means that you cannot ship to this store from this distribution center within 24 hours. So this matrix over here shows you if it is possible to ship items from a DC to a store within 24 hours. We usually name this table as AIJ. If AIJ is 1, it means that from I to J you can ship. Okay? Or from, let me say, stores is I and distribution centers are J. From J to I you can ship these products. Now, what we want to do, we want to establish, okay, in this question, let me write the question, locate, let's say, minimum number of DCs to serve all stores within 24 hours. This is the problem. Okay, so let me illustrate. This is store 1. Okay, in order to serve store 1 within 24 hours, you see there is this alternative. If you establish a facility in DC in candidate location 1, then it is possible to serve. If you don't locate this, of course you can locate here. If you don't locate here as well, then there is another alternative. You can locate it here or here or here. So if you locate in one of these distributions or one of these candidates 1, 2, 8, 9 and 10, then it is possible to serve this. Otherwise, if you don't locate to any one of them, don't locate here, don't locate here, not here, not here, not here, as you can see, the remaining alternatives cannot reach this store within 24 hours. It means that you will not serve store I within 24 hours, but it's a requirement of the problem. All these stores must be served within 24 hours. But if you compare store 1 and 2, actually the data for them are different. So for the first store, you have to consider establishing a distribution center to 1, 2 or 8, 9, 10. But for store 2, it is only 1, 2, 3. So the others do not help in satisfying the need or request from store I. So therefore, I need to write constraints to satisfy this. But first of all, we will formulate this problem. And in order to formulate it, we first need to define our decision variable. Let's define it. What should be my decision variable? What am I trying to decide on? This also is similar to the previous one, but if you can see, there is no allocation here. There is only location, not allocation. So when we, for example, locate a distribution center to this candidate site, then any store that has a 1 in this matrix will automatically be served from here. Okay? So if I establish a DC to location 2, then store 1, 2, 3, 7 and 8, I will be reaching them. Okay, but you see, with just this one, I will not be able to reach these customers. So actually, opening just one distribution center is not satisfactory at this location, I mean. So in order to reach the others, let me say I am going to open this one, a second one. And if I open it, you see, I can reach 4, 5, 6, okay. I can reach 7 and 10. But this 9, still I cannot reach 9. I am not trying to give you the optimal solution. I am just giving you a solution. Okay, I am just trying to find, okay, what can be an alternative solution. And in order to satisfy this demand in 9, actually there are alternatives, like I can open it here, 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 or here, or here. You can select any one of them, and when you select one of those, the demand of this 9, store 9, will be satisfied. Let's open to location 4. So when I open to location 4, you see this store 3 can be served here, store 5, 6, 7 and also 9. Now as you can see, for each one of the stores here, I have at least one distribution center that can satisfy the demand. But have a look at this store number 3. Store number 2, I opened it and it can serve this one. And store number 4, I decided to open it and it can serve. Now, what is the situation? Which one will serve? Actually, we are not interested in that one. This store number 3 can approach to any one of these and ask for items, and they will be ready for serving. We are not deciding on which one of them will be serving there. Think about this question. You can think about this question from another perspective. All of us now using mobile phones, right? And our mobile phones, in order to have this service, they need to communicate with base stations. And the base stations are usually on top of such towers, okay? And they are located at different places around the city. And for example, if these base stations have a radius for their signals, okay, their signals can reach up to a certain radius. And depending on their power, this radius can be larger or smaller. The thing is, the areas that are within these circles are covered. If you are, for example, currently here, none of the signals reaching you, it means that you are not taking any service. Okay, for example, if you are here, now this circle of this base station reaches you as well as this one, and it means that you are covered by both of them. Is this a bad thing? No, it's good. I mean, you can communicate with any one of them. But what we want in covering problems is, we don't want to have such a situation so that there are some customers which are not covered. If a customer is covered by 2, 3, 4 facilities, no problem, it's okay. But we are not deciding on, okay, this is covered by 2 facilities. I decide this facility or this customer to use this facility. No, we are not deciding on it. Whichever he likes, he can use. That's it. Therefore, if a facility is covered for more than one, then it is preferable. It is not something we don't want, and it is not something we decide on. Therefore, here we have only a single type of variable. And what is that variable? Whether we establish a facility at site or not. So it is yj if, let's say, a facility is opened at site j, and otherwise it will be 0. It is just this. Okay, then there is no allocation, so I don't need xij. On the other hand, I want to establish the minimum number of distribution centers. So this gives me my objective function, minimum number of distribution centers. And remember our previous formulation for the P median and P center. In those problems, we said that we are going to establish exactly P facilities. And in order to write this constraint, we took the summation over yj and we set it equal to P. In this problem, we don't know, we don't want to open P facilities, but we want to open minimum number of facilities. So therefore, again, I need to take the summation j from 1 to n. In this example, remember how many candidate sites for the distribution centers we have? We have 10. It will be j from 1 to 10, yj. And we want to minimize this. Okay. Then objectives. What are my objectives? And if you remember Operations Research 2 course, we have very specific constraints for the covering problems. And what is that? We write a constraint for each one of the customers. In this case, the customers are the stores or the existing facilities. Okay? So what do we say? If you want to cover, if you want to satisfy the demand of this customer, Either there should be a facility in 1. So how do we understand if there is a facility in 1 or no? It is y1. Or there must be a facility in 2, so y2. I cannot use y3 because even if you open a facility in y3, you will not be satisfying the demand of this customer. So just ignore these zeros. And or you should have a facility in 8 or 9 or 10, and at least one of these must be 1. At least one. If all of them are 0, okay, then it is not possible to satisfy the demand of this customer. If you write this equal to 1, then it's problematic because you are here saying that it is not possible to cover the one customer with more than one facilities. But remember this tower example, the base station example. There's a base station here with signals like this and another one signals like this. So how can you arrange, how can you say that no, this region, it is not allowed, you cannot do it? No, they are just providing signals, okay? And it is possible. So no problem having more than one. So what do we need to write is it should be greater than or equal to 1. And this constraint is a constraint to satisfy the demand of store 1. What about store 2? Again, for store 2, I need to check the ones. Look, this is y1, this is y2, this is y3, and this is y10, corresponding variables for the candidate sites. Then, for the second candidate, I am simply multiplying these ones with this one with this one with this, and remember there is y4 here, and I'm multiplying this value with this y4. I'm multiplying this value with y5, and if it is 0, it just disappears. If it is 0, it just disappears, but if it is 1, it is inside the summation. Okay, so simply I'm multiplying this row with the decision variables. And in order to write this in a compact form, if I define a parameter which will give me these zeros and ones, actually it is this parameter, okay, aij. So simply I am writing for each existing customer I from 1 up to m, I am summing up these yj values, but I am summing up after multiplying with aij. So 1 times y1 plus 1 times y2 plus 1 times y3. So these are the aij values, and I am taking their summation over 1 to 10. These are the new facilities. And I want this to be greater than or equal to 1. For each of them, it should be 1. So instead of writing this in open form in this way, I can easily write it in such a compact form. Okay? And what else do we need? Actually, nothing. Just yj greater than or equal, yj are binary. Not greater than or equal to 0, but binary decision variables. This is how we formulate the total covering problem. Okay? A version, just last thing, final thing about total covering, a version of this total covering, instead of minimizing the total number of DCs, which is this objective, sometimes we try to minimize the total cost of opening facilities. Okay, not the number but the cost. And it means that we have a cost parameter Cj. Cj is the cost of opening a facility at site J. So in that case, we just replace this objective with This one, j from 1 to 10, cj times yj. Okay, so this version here just minimizes the number of facilities. This version minimizes the total cost of opening the facilities. The only difference is this, and both of them are called total covering.